Hello everyone and welcome back to our course on microprocessors and microcontrollers. I am Sahil and as I mentioned earlier, I have completed my Bachelor of Technology in Electronics and Telecommunication Engineering from VIT Pune, and currently I am pursuing my Masters in Technology in Computer Engineering from Veer Mata Jijabai Technological Institute in Mumbai. In this course, we are systematically building a strong understanding of microprocessor architecture and programming. In the previous lecture, we introduced 8085 microprocessor and we discussed its basic features including the 8-bit architecture, 40-pin configurations, 64 KB memory accessing capability and its evolution from earlier Intel 8080 processor. This gave us a solid foundation for understanding how the 8085 operates as a basic computing device. In today's lecture, which is lecture 7th of this series, we will focus on one of the most important aspects of data processing and instruction executions. By the end of this lecture, you will understand the register set of 8085 microprocessor, the role of accumulator, the importance of program counter, stack pointer, the structure of flag register, and how the flags such as 0, sign, carry, parity, and auxiliary carry are used in ALU operations. Now, without further ado, let us begin with the concept of registers. Registers are small but high-speed storage locations located inside the microprocessor. They are used to temporarily store data, instructions, and address intermediate results during the process execution. Because of registers are part of processor itself, they are much faster than accessing the external memory. The Intel 8085 has a set of general purpose registers which include B, C, D, E, H and L. Each of these registers is 8 bits wide, meaning they can store 8 bits of data. These registers can be used individually to store data, or they can be combined into register pairs to handle 16 bits of data as well. The common registers pairs are BC, DE and HL. For example, a program needs to store a 16-bit of memory address. It can use the HL register pair where H stores the higher 8 bits and the L store lower 8 bits. These general purpose registers are used for data transfer, arithmetic operations and temporary storage during the instruction execution. Among all these registers in 8085, one register has a special and very important role, which is the accumulator, often referred to as the register A. The accumulator is an 8-bit register that is directly connected to the arithmetic logical unit or ALU. Almost all of arithmetic and logical operations in the 8085 involve the accumulator. For example, when there are two numbers to be added, one of the operands is usually stored in the accumulator and the result of the operation is also stored back into the accumulator. Similarly, logical operations such as AND, OR and XOR are performed using this accumulator. Because of this central role, the accumulator is considered to be the most important register in the 8085. Now let us discuss two special registers that are essential for controlling the program execution, which are the program counters and the stack pointers. The program counter or PC is a 16-bit register that holds the date address of the next instruction that is to be executed. As the processor executes instructions, the program counter automatically updates into the point to the next instruction in the memory. This allows the processor to execute a program sequentially. However, in such cases such as jumps, loops or conditional branching, the program counter may be modified to point a different memory location. This enables the processor to control the flow of program. Without the program counter, the process would not know which instruction is to be executed next, making the program execution almost impossible. Another important register is the stack pointer or the SP. The stack pointer is also a 16-bit register that holds the address of the top of the stack. The stack is a special area in the memory for temporary storage of data, especially during the function calls and the interrupts. When the data is pushed onto the stack pointer is updated to point the new top of the stack. When the data is popped from the stack pointer moves back accordingly. The stack is used to often return address intermediate data, and register contents during the subroutine execution. This makes the stack pointer essential for managing the nested function calls and the interrupt handling as well. Now let us move on to another critical component of 8085, which is the flag register. A flag register is a 8-bit register that contains information about the status of the process after the arithmetic or the logical operation. However, not all the bits in register flag are used. In 8085, 5 bits are used as flags, while the remaining bits are unused. The 5 flags that are used in 8085 are sign flag, zero flag, auxiliary carry flag, parity flag, and the simple carry flag. Let us understand each of these flags in detail. The sign flag or the S flag indicates whether the result of operation is positive or it is negative. In binary representation, the most significant bit determines the sign. If the most significant bit is 1, the result is considered negative, and the sign flag, it is set to 0. The resultant is positive and the sign flag is then reset. The zero flag or the Z flag indicates whether the result of an operation is 0. If the result is 0, the zero flag is set. Otherwise, it is reset. The flag is very important in decision-making operations such as conditional jumps. The auxiliary carry flag or the AC flag. It is mainly used in BCD arithmetic operations. It indicates whether there is a carry from the lower nibble, which is the lower 4-digit bits, to the upper nibble during an arithmetic operation. The parity flag or the P flag indicates whether the number is ones in the result is even or odd. The number of ones is even, the parity flag is set. If it is odd, the parity flag is reset. This is useful in error detection and the data communication. The carry flag or CY flag indicates whether there is a carry out of the most significant bit during an arithmetic operation. In subtraction, it becomes a borrow. The carry flag is very important for multi-byte arithmetic operations. Now, let us understand the role of flags in the ALU operations as well. Whenever an ALU operations performs an arithmetic or logical operation, it is not only produce a result but also updates the flag register based on the result. For example, if an addition operation results in the value that exceeds the maximum value that can be stored in 8 bits, the carry flag will be set. If the result of the operation is 0, the zero flag will be set. These flags are used by the processor to make decisions during the program execution. For example, during the conditional jumps, instructions use the status of the flags to determine whether there is a jump should occur or not. For example, a program may need to include a condition such as jump if 0. In this case, the processor checks if the zero flag is set, and if it is set, the program counter is updated to jump to a specified location. Similarly, instructions such as jump if carry or jump if sign depend on the corresponding flags as well. Because of this, flags play a crucial role in implementing the decision-making loops and control structures in the assembly language. In summary, the registers and the flags are essential components of 8085 microprocessor. Registers provide fast storage for the data instructions, while the flag provides important information about the result of operations. Together, they enable the process to perform calculations, store immediate results, and make decisions during the program execution. Understanding registers and flag is extremely important because they form the foundation for writing the efficient assembly language programs. And that brings us to the end of lecture 7, that is the registers and flag in 8085. Today, we studied the general purpose registers, the accumulator, the program counter, and the stack pointer, the flag registers and roles of flags such as zero, sign, carry, parity, auxiliary carry in the ALU operations. In tomorrow's lecture, we will move forward and study the instruction cycle and the machine cycle in 8085 microprocessor. We will understand how the instructions are fetched, decoded, and then executed, and how the timing plays an important role in these operations. If you are enjoying this course and want to continue learning about microprocessors and assembly programming, make sure to subscribe to the channel and stay tuned for the next lecture. Until then, thank you for watching and I will see you in the next lecture. Subscribe to my channel and follow me for more such content on engineering and physics science. Have a great day.